Hello, and welcome to Class 8 of Particle Fundamentals and Fuzzy Logic. So in this class, we're going to think of these things more as a group instead of an individual, and try to get some appropriate variation, as well as set up several test scenarios to test each aspect, each important aspect that's relative to the global look of our simulation. So we'll go through a bit of how we might go about doing that before application to a final shot. So here's where we left off in the last class. And we see we have a bunch of sharks, and right now they're all just doing the same exact thing as the target changes. You know, we really can't see much variation at all, other than just their starting positions. Okay. So the first important thing we want to do is, before even the particle simulation, is that we want to take a look at the scale, because scale is one of the most fundamental things to any set of particles, whether it's an inanimate object like rocks, or whether it's a crowd such as this. I'm going to start off by making a few more sharks. You can never have enough sharks. All right. Okay, there we go. All right, so let's put some scale variation in here. And we might be surprised by how intricate this process might be. It's often the difference between an effect never feeling right or, really portraying itself in a realistic way. So what we want to do is we want to adjust the copy scale, the point scale. So I'm just going to start off by exporting a p-scale parameter. And that'll feed all the way down into the copy. Okay. Now, bringing in something like the ID, or in this case, they don't have IDs, so we could bring in the point number. And if we just do a random, which we've all probably done, uncheck that, and we just pipe that into the p-scale. Okay, so we clearly want to fit that range, so following that random up with a fit. So we know what's coming out of the random is a 0 to 1 value. So let's sculpt these ranges a bit. I'm going to give this a destination minimum and a destination maximum. Let's call this min output. And maximum max output. And the interface level. So generally what I would want to do here is find the minimum first, minimum specified size. And because this shark was based on a realistic scale, we're going to find something that's pretty common in, I think, most crowds anyway, is that here's the baseline, and we really wouldn't want much smaller than 80%. And, maybe even push that a little bit, but let's leave it about here. Now, for the maximum output, we can do the same kind of thing. And it's not really going to go much beyond 1.2 or so. So this looks like an okay variation of size for a crowd. But as we add a little more even still, we're going to notice something a little funny. Let's really accentuate this scale just to see the differences here. Okay, so all of a sudden this crowd isn't really looking that realistic. And there's just something off about it. So what is that? Well, most life forms follow a very distinctive curve as for their crowd distribution. So you're not really usually going to see very many little ones, and you're not going to see very many big ones. you're usually going to see something where the focus is clearly in the middle of the range. Okay, it's usually different for inanimate life forms. So let's just take a look at that. All right, so as we get these random numbers out of the curve here, and let's remap this with the, let's remap the random with a curve. Call that curve. Okay, so that's what we had before. Now, if I were to pull away from this curve and really have the focus on the low range here, let's do that with a B-spline, then it looks even weirder. So this type of a distribution would be something we'd use more for inanimate objects. So following the rule of entropy and just how rocks and various things would break and shatter, you're probably not going to find too many big rocks, for instance, if you're walking on the beach, but you're going to find progressively more and more and more smaller rocks. So this would be more of an inorganic distribution. Now we want to give this more of a lifelike distribution. So what does that mean? Well, we're going to focus, instead of the low range or a linear curve, which I don't think ever looks good for almost any effect you're going to do, we're going to focus on the mid-range here. All right, so now that's looking a lot better. Okay, so nature kind of dictates, and this is the same in population growth and all kinds of other phenomenon, is that most of the time traits, factors, and even natural selection, it's not going to have too many sharks, for instance, that lived to an old age and grew up to be a super shark, and you're not going to have too many giant sharks in general. They're going to follow more or less what their genetics tell them to do. And likewise, you might have a lot of sharks that are born, but then, most of them are going to die out before they reach a middle age. So this looks like one of the smallest sharks here, and that's not going to happen very often. Okay, so let's focus that a little bit more on the medium range. Okay, and I think my low values are looking a little bit too low, so let's bring that back up. Okay, and the high values, a little bit too high. All right, so that looks like a really nice natural distribution, and we didn't have to do too much beyond, what we've already done as simple techniques, but it makes a huge visual impact to our work. And people could look at a shot like this over and over again, and they'd never really know exactly what the problem was with it. And it's really more of these subconscious cues, I think, because instinctually, I think we're all used to observing nature because we have since we were born. And one of the beautiful things about working in Houdini is we don't have to go through this entire process over and over again. Let's modularize this and make this a tool that we can use in SOPs as an asset to give us variation very quickly and easily on any parameter. And it's really going to add the life to our effect here. So as far as what attribute is set, let's not use this anymore. Let's use a set attribute. And I want to be able to choose what attribute I'd like. So here's that. And this is actually totally fine for the name. Let's start though with p-scale. Okay. And as for the pointer primitive number, this will be exclusively for points. So I'm going to plug this in. Attribute type, this wouldn't be particularly useful for vectors. So I'm going to make a float. Okay. And in comes the value. All right, so that's doing the same thing. And we also want to be able to add a seed because what we don't want is we don't want to have two completely unrelated parameters, and then to make a change in one of them, and we have, like, for instance, very small sharks, and then we do the same exact process with the same random for a different variable of the sharks, such as speed, and it'd be really weird if all the small sharks had more drag on them, for instance. That just seems like they'd have less drag. So we don't want to intrinsically tie our randoms together. Because everything is per ID or per particle. So let's add a seed to this. And we want a little bit more variation anyway, because we could have been using this exact thing for somewhere else in the scene. Okay, so let's make a parameter for seed. There's our seed. And I'm going to do an offset of that. Something sufficiently random using a multiply add constant. And now let's add the seed to the point number. And let's also use a multiply add constant for that. So this will be a different random offset. Okay, adding those together. Let's do an integer to float on this. Okay, so we've got a nice floating point random number going into here. And let's test that out and see if it works. Yep, seems to work just fine. All right, and if you know you really have the settings right, if any one of these random variations works pretty well. All right, now setting the same seed on two identical streams. So for instance, if we were to copy this and use it downstream for something else like drag. Okay, so now we can see we've got the same amount of drag as p-scale. So we could just change the seed. Now, instead of that, I don't want to have to keep track of seeds, and I don't want to have to use something downstream. So I want some type of an import and export mechanism for what I do, because I want to choose whether they're related to one another. I might also even want to use the result of this curve, or I want to choose if they're completely unrelated to each other. In this case, I can change the seed. All right, so let's set that up a little bit. Okay. So I want to give this another attribute that's being exported, and we could do that out of the curve. So let's use another set attribute, and this time it's just going to export a 0 to 1 value out of the curve. And for the attribute, let's call this export attrib, or we could call this export curve attrib. There we go. And let's call this gradient. Okay. By default. So there we go. So now we have the actual attribute we are after, and that's after the fit. So these are our actual values we want to use. And then we also have a really nice relative value. Okay, so the size here is relative to the largest size. So we can see that up here on top, we've got almost 90%, and that's a p-scale of this. And then at the bottom, we've got that, and that's a p-scale of this, one of our low values. Okay, so this might be really useful to work with. Cool. And we might even want to give this a color preview, but for now, I'm just going to leave that out. Okay. The final thing is, what if I actually want this value, this seed value, to drive a different ramp, but I don't want to have the curve baked into this. Okay. Want maybe use a different curve, but the same identity or the same seed. So in this case, we could export directly out of the random number. So I'm just going to copy that. And let's say export rand attribute. Okay. So that'll come directly out of our random number. And let's make this a tool. We'll call this fuzzy random distribution. And let's just put this in the scene for testing. All right, so here I'm going to start off by just promoting this to the asset level. There we go. So now this is a fairly lightweight tool that's quite easy to copy and paste and do this many times for different types of settings. I also just want to give this a quick enable and disable attribute. I've gone ahead and made defaults grad underscore the attribute name, but I would like to enable and disable those. So I'm just going to drop down a quick if statement so we don't have just tons and tons of attributes on our resulting particles. So here I'll just do an if block. And let's connect this to the handle. And then let's make a parameter to enable the and export attributes. There we go. There we are. And now that we have a digital asset to quickly manipulate these values either in a controlled way or an uncontrolled way, let's use this for something other than the size, although the size will be a really determining factor that will affect the rest of the groups. So we'll call this fuzzy p-scale. All right, and this is fine for now. And now let's come up with a test scenario and really tweak our trajectory, our movement as it seeks the target. And let's really nail the value and the balance of different factors that cause it to accelerate into the target. I think it's really important to come up with representative test scenarios and to work in order of importance with a particle effect, because a particle effect is really hard to control once there's more than a few factors in there. So we have to kind of analyze what is the most important factor that's going to define this crowd, and then work backwards to the least important factors. If we try to do all the factors and tweak them at once, we'll end up with a giant mess. So, okay, so here let's make a simple test scenario that'll take under 5 minutes, and let's have about 20 sharks. Okay, so here's our starting position. And now let's have a target for the end position. Right about there. And now I just want to switch between this and the original. So I'm going to use a switch. Okay. So first is that, second is that. And let's just have it switch every 10 seconds. So I'm going to do a floor of the current time divided by 10. And what that's going to do is it's going to, until it gets to actually 10 seconds, it'll stay at 0. And then once it passes 10 seconds, it will increase just by 1. Okay, so there we go, 0, 1, 2. And then finally, let's just do a modulo of 2 for that to make it switch 0, 1, 0, 1, because modulo is the remainder. Okay, so our targets will, our source will be here, and our targets will be here. Okay. And now we can really see how fast these guys are moving. Any variation we're seeing right now isn't due to any source attribute or ID. It's due to the noise in the system, the noise in the ocean current and in the various vectors, the environmental factors that we added in the previous class. So it's a certain degree of variation, but it's not that much. Okay, so now let's test this out. Let's really get a good set of values and then add some variation based on the size of the shark. All right. So in our particle system, I'm just going to take out any global factors just so we can really get a representative for the look. So if the target up vector that's being set based on the ocean current, I'm just going to disconnect that and uncheck invisible and make sure that's set to a good default and export always. So that's disabled. And then let's take out any global ocean current. And now there actually shouldn't be hardly any variation other than their starting position for the sharks. And yeah, creepily, it's almost uncanny how varied all of these settings were as they were playing against each other before, even with simple water current. And now the differences are non-existent, and we can see their different sizes, but they're all moving at exactly the same speed. Okay, so let's get a good set of default values for that. Okay, so I'm going to go to the seeking behavior, and let's really test to see how far away we're detecting as our threshold for, now that we've got our whole system essentially built, let's really fine tune the seeking behavior values. Diving in, I want to make a better preview mechanism. So let's use test A as a preview vector. And I just want to clamp what's driving the distance, and that would be shark seek distance high. So I'm going to clamp our target distance to only be potentially that high. And then let's use the target vector, normalize that, and multiply this normalized vector by the value. Okay, let's see what that looks like in a preview. Okay, so here this should be about shark seek speed high. No, we're after shark seek distance high. That should be about 5. And now see that it's a much nicer preview mechanism going on here. We can also see the color represented in their swim pulses, but for now I just want to get a little bit of a color preview going here too. So let's get this color. And let's use the result of our seeking ramp to drive how interested they are. Let's see how that plays out. Okay, so they're really interested, it's red, and they decrease their interest going to blue. Okay, so now let's actually fine tune these values. What do we think here? So based on kind of like the size of these sharks and the speed that they're going after, I'm just going to turn off the drag, the overall global drag. Okay, so they really take off here, but I just want to test the speed. And I think they should even have quicker acceleration than this. but maybe they reach their maximum speed sooner and they coast, and we want some water resistance, obviously. So first, let's examine what's contributing to the speed. So that'd be the pulse rate. Okay, so let's just turn off the test A. I'm going to turn on test B here. And let's try to get a visualizer for the pulse rate. I'm going to multiply the target direction by the scalar going into the velocity add, the very last step. And let's use a preview mechanism, test B. There we go. Okay. So the first thing I'm going to ask myself is, okay, they're really excited. Are they swimming? Like if each pulse represents left and right motion, is that really them taking off? Okay, so maybe we could even push that a little bit higher. Okay, that's fine. And now I just want to add to the pulse. Let's get a pretty good baseline value. Let's add 3, see where that gets us. Okay, so that's not very fast. And let's try without any drag. Keep this in mind, 10. Okay, still not the acceleration I'm after. Maybe 20. Yeah, okay. And that's even a little too high. So maybe I'm going to settle somewhere around, 13, or push it even a little bit more to 14 or 15. Okay, so this is my high acceleration value. Okay. And then let's turn on the drag here. Oops. And let's get a good drag value. So they're really not responding that well to the drag, and this isn't really like definitely going forward. They're not going to hit much resistance because they're so aerodynamic. So let's try half of that. And often it's good to work in fractions as we're verifying our forces here. Okay, and 0.25. And yeah, they really took off, but then they leveled out their top speed. And that's really what I want to see. I might even ease off that just a touch more. There we go. Okay, now the addition of the pulses when it's near, we probably shouldn't be swimming much at all, but every time it moves its tail, it's going to have a little bit of a pulse. So let's set that to 0.5. Okay. Okay, and now our pulse rate is through the roof as it is near. So let's just say it's always going to be swimming maybe 1 pulse every 3 seconds. So that could be 0.33. There we go. So I think it's actually functioning best when it's around 0 for the close-up pulse. Okay. And now we've got a pretty good set of values. Maybe a touch more drag. So now we have a pretty good set of values. Let's add some variation. And that's really where we're going to see the magic happen. Okay. So let's get back to our test A visualizer so we can see the close and the far. And so what I want to do is I want the small sharks to basically be more frenetic and to swim faster, have more acceleration than the big sharks. Okay, so we want to do that all based on the p-scale. So I'm going to export, find a seed, and export the random attribute and the curve attribute. And dropping down another fuzzy rand distribution. I want to use the grad p-scale which it represents the exact proportionate size of the shark, and I want to use that to drive this curve. I don't want to use the seed, or at least not very much. I don't want to use the random very much. So that means we have to import that attribute somehow into here. So a little modification to the digital asset. Let's make an attribute to drive that value. So I'm going to use a get attribute so that we can set the name. And I'm going to make a string parameter. I'll call this driver attribute. And string. All right, so that'll be the attribute. We are after a float. The input would be itself, the first input, and the point number would be the current point number. Okay, so here's our driver attribute. So instead of using 100% or none of either this coming in or our new random seed, I want to do a mix here. So let's make another setting. So here's our random coming in. That'll be our default behavior. And then this is our behavior that's set from above. And here we'll just say mix driver attribute. And the driver attribute, I'll also have this default to grad. Okay, so instead of our random exclusively driving the curve, we'll have this driving the curve. Okay. So let's accept that. All right, so now this one also has those driver settings. Actually, we have to add them. There we are. And reading this in here, the driver attribute, so I want to have this driven by grad p-scale. And I want the small sharks to have a higher acceleration than the large sharks. And here I've gone ahead and made a preview mechanism in the normal with a point wrangle. So I'm setting the normal to pulse intensity high in the X. So here, I'm going to set this to pulse intensity high. And if we just look at our random seed here, we've just got, let's say, 0 to 1 values of pulse intensity high, but we actually want the minimum value that we could attain, not just 0, so based on size. So here, let's take another look at these particles. And we found our maximum acceleration, but now I'm interested in the minimum. So let's just remember that that is 14. And so let's go after the minimum here. Let's say what a really big shark is going to be swimming. And okay, it's a little slow, a little sluggish. Maybe try 10. Okay, so I'm satisfied with that. Okay, so we know that the minimum, or the maximum, is going to be 14, and the minimum is going to be 9.4. So back here, 14 and 9.4. Okay. So we can see our variation, and adjusting the seed, we see that. But we actually want to drive this based on grad p scale, and we want the smaller sharks to have the most. So if we manipulate this ramp a little bit, we'll see that only a few have the high value. And now I'm going to mix, that's based on the random. And now I'm going to mix in the grad p scale. And you see, what we should be seeing is that only the small sharks are going to have this quality about them. Okay. So now let's do something that we want with this. So here we're bringing in the grad p scale. And then let's see, how is this going to play out? So I think the small sharks will actually be a lot faster than the big sharks. So here, I'm going to give this an emphasis. The small ones are going to be quite active, and the larger ones are going to decrease their activity fairly gracefully, like that. Okay, now if we wanted to mix in a little bit of variation, right now we're not mixing it at all. Now let's taper off this value. So let's say that about 75% of the qualities are going to be based on the size of the shark, and then we want a little bit of quality based on just a purely random and yet distributed behavior. Okay, so now let's try this out. So as I plug this in, okay, so let's observe the quality when the sharks are simply swimming along uniformly. And now as I plug this in, one of the beauty of proceduralism and attributes is these attributes are going to propagate through the system, flowing all the way down, getting all the way down into here, and then overriding this pulse underscore intensity underscore high value. So now the little ones really took off. And that's going to add a lot of interest to our effect. I mean, even without the environmental forces, we've just got so much more variety going on here by one simple addition into our system, one simple active variation. So we've added that. Let's turn back on our global forces and our up behavior. And we've already got a lot more realism going on. So in the next class, we're going to come up with some rotational tests and some dynamic variation, meaning within the simulation, to finish off the variation component.